Good morning. Welcome back to Physics 4C Lab. Today in lab we're going to be looking at measurements of the Planck Constant. So in class we've been talking about the photoelectric effect as one of the early successes of kind of a Planck model for how frequencies and wavelengths of light depended on energy. And so we're actually going to be using that photoelectric effect that we've been talking about to go and get a measurement of the Planck constant. Now, the photoelectric effect works this way. If we have a sample of some material, and the photoelectric effect is pretty easy to show in metals. So metals have electron binding energies that are in the range of a few eV. 2 or 3 eV worth of energy is enough to remove some electrons from a piece of metal. Now, of course, the binding energy for electrons in metals, it's not the same for all the electrons. Some of the electrons have much higher binding energies than others. So if we shine light on a piece of metal, there's a minimum amount of energy that those photons in the light need to have in order to have electrons that separate from the metal. So the way the photoelectric effect worked is you could build these vacuum tubes. You could place a piece of metal inside there. You could shine light onto the metal. Now, typically, if the light were coming in from, say, the red part of the visible spectrum, the red photons didn't have enough energy. Red photons only have energies of 1.7, 1.8 eV, something like that. That's not enough energy to overcome binding energies of electrons in typical pieces of metal. So you have to have energies, again, of something like 2 or 3 eV, and that means typically you need to be either into the green or maybe blue part of the spectrum. For most metals, that's where the binding energy is going to be. So we're going to need to have photons with at least that much energy up front, or at least that much energy as a minimum, in order to have the electrons leave. Now, if we shine higher energy photons, maybe something in the blue part of the spectrum, those electrons are going to be coming off with larger and larger kinetic energies. So the idea then is, well, let's look at it this way. Here's the kinetic energy of the electrons that are coming off in the photoelectric effect. It depends on the energy of the photon minus whatever the binding energy is. So let's say, let's put some numbers in here and imagine what this might be describing. Let's say that the photons are coming in with 2.5 eV of energy each, and the binding energy is 2.1 eV. Well, then the kinetic energy of those electrons we would expect would be the math right here, 0.4 eV. So something like that. That's describing how much kinetic energy the electrons would come off with. Now remember, some of the electrons are attached more firmly, so as we increase the energy of the photons, we're going to get more and more electrons coming out. All right, so that's the photoelectric effect. Now, what we can do then is we can take the energy of those photons and say that the energy of the photons are related to the frequency. What we can do is for the energy of the photon, we can substitute in h times the frequency. And then over in our table, the frequency can be determined using wavelengths. And so what we have is we've got, well, we have a light source here. Let me see. All right, I'm turning this on. We'll take a closer look at this setup after we look at the board here. But I've got a light source. I have a photo tube right here. And right now it's got a blue filter attached. So by blue filter, that means that it's allowing the highest energy photons to come in. So when I shine this white light, Some of those photons are going to have, they're going to be from the blue part of the spectrum. I'm going to be able to, or the photons that are coming in are going to have quite a bit of energy, and that means that inside the phototube, we're going to have, where is the picture? Here it is. So here is our power supply that we have set up. Power supply is right here. We have a circuit set up with the phototube and an ammeter. So the idea here is that we'll get a power supply. Now the power supply is able to create a reverse voltage. So the voltage supply here is going to be variable. We can turn the voltage way down so that there's no voltage going on at all. And that says when we have light shining on the phototube, we're going to get electrons that transfer from one side of the phototube to the other, and those electrons are going to be able to make their way through the circuit. Now, in order to prevent the electrons from crossing, what we can do is we can turn up the power supply. So as we turn up the power supply, we can keep track of that voltage difference. And as the voltage gets larger and larger, it's going to be harder and harder for the electrons to make their way across. And it actually looks like with the directions I've got here, I think I need to switch my power supply signs. I think I had that set up oppositely. So what we're going to do is we turn up the voltage source. This side is going to become more and more negative, and that's going to prevent the electrons from making their way across. Okay, so the plan is this. The plan is that we're going to use a series of filters. So what I've got, I have some blue filters, I got some red filters, and I got some green filters. And what we can do is to check what part of the spectrum these filters are allowing to go through. What we can do is we can put these up next to a diffraction grating. Now remember, the diffraction gratings are going to give us kind of rainbows effect from the light. Let me just turn the lights off in here or dim them. This might be too much, but we'll see. So what I'm going to do then is I'm going to take this diffraction grating. I'm going to hold this up to the light source, which is right here. And you know, I can see the whole spectrum. So I can see the red, orange, yellow, green, blue, violet. They're all there because, you know, that's just an incandescent light bulb, and that's going to create the entire range of wavelengths. Now, if I take the blue filter, what I'm finding with the blue filter is it is letting through only the blue and the green end of the spectrum. The reds, the orange, the yellows are gone. Now, putting the blue filter on then is going to let the highest energy photons get through. So now, for the blue filter, I'm saying that it's allowing photons of wavelength 450 to come through. And then I can calculate their frequency here, C over lambda, 6.67 10 to the 14. And so I have taken this, again, I'm going to look at my rainbow here, look at my blue filter, and I can see what part of the light is being allowed to come through. And it goes all the way to the violet end. In fact, I'm thinking I'm going to have to redo my data table. This looks like it's allowing photons all the way down to 400. Certainly looks like that. All the way down to the edge of visible light. If I grab one of my green filters, same idea. What I'm doing here is looking at the full spectrum, this entire rainbow. When I put the green filter on, it blocks out the blue light. So the blue light is pretty much gone, and we're down to where we just have the greens and the yellows. The red and the blue is gone. So for this filter, when I'm using this filter, the photons coming in are going to have less energy than with the blue filter. So this is a 400 nanometers. I'm thinking I'm going to move this to 500 nanometers. You know, just looking at the portion of the filter that's going to come through. So that, I'm probably going to be making that change. So when you guys get the data tables, I'm guessing this is 400, 500. Let's get the red filter out and see what the red filter is blocking. And yeah, the red filter is very, very good at blocking out the blues and the greens. So I've got some reds and oranges and some of the yellow, but the green and blue part of the spectrum is just gone. And so when I've got the red filter on my light source, the highest energy photons coming through are going to be limited to a wavelength of probably around 600. Again, I'm going to double check these filters with some spectra. I actually have a chart here. Let me just grab it real fast. Here is where I have been checking my filters. So I have a chart, and this is not anything. Well, let me use this one actually. Here is my visible spectrum, and here are the wavelengths listed on here. And when I get out that diffraction grading, I can see the entire spectrum. So I can see from 400 out to 700 easily, and the blue filter is taking all of this out. So the highest energy photons are going to be around 400 nanometers. The green filter is taking on, yeah, actually the 500 works pretty well for the green filter. And the 600 works really well for the, so I'm changing those numbers for sure. Yeah, I'm not sure why I had those in my, I had both sets of numbers, and for some reason I was thinking these were the right ones, but I think I'm going to get those changed. So anyway, I'm using that visible spectrum from my reference chart, and I'm going to, well, I'm going to switch these numbers over, and that's going to change the frequencies too. So you will see all those numbers updated in Canvas when you take a look at the lab notes. All right, so I'm going to unplug this and get the lights turned back on here to the front of the room. So what we've done now, we've identified 3 different light sources by using 3 different filters that we can use to activate. And I'm going to move this out of the way too, so you guys can see the setup a little bit better. All right, so now if we take a look at the circuit here, we've got this power supply setting up what's considered to be a reverse voltage. So what we'll do for each one of the filters, we're going to do a graph. What we're going to do is we're going to turn this on. So here I am turning everything on. And when I turn everything on, what I can see is that I'm getting current flowing through the circuit. So that is, that's being generated from this phototube. So that phototube is generating a stream of electrons and generating, well, the electrons are going this way, a current of electrons going through the circuit in this direction. Now, what I want to do then is I want to start off with my power supply shut way down. So I got my power supply at 0, and here is my voltmeter, keeping track of how much voltage the power supply is producing. It's not right at 0, but it's very close here. It's at 0.3 millivolts, so that's pretty tiny. And then what I've also got is I have a current. So I got a current of, now I've adjusted the intensity of light, or I'm going to adjust the intensity of light, so that at 0 volts, I'm always starting at 100 nanoamperes. Okay, so I'm going to start at 100 nanoamps. And then as I increase the voltage, the stopping voltage, that should be able to shut down this current. Fewer and fewer of those electrons are going to be able to make it across. And that means that the current should drop off. And here are some data points that I'm imagining I'm going to see. Now, what I can do is I can show you, here's my ammeter right here. And as I turn up the voltage, I'm seeing less and less current. Now, what's very important right here is this threshold. Hopefully you can see this. We'll do a close-up. As I adjust the voltage, the current shuts down. That's a little complicated to get the exact stopping voltage at which the current zeroes out. So what we're going to do is a series of measurements, and then we'll do a fit. Now, over the years, we've tried different kinds of fits to estimate where that stopping voltage occurs. So the question here is, at what voltage does the current reduce down to zero? So we're going to do some data tables. Here is the voltage. I'm going to increase the voltage here from 0 to 0.2 to 0.4 to 0.6, and then I'm going to keep track of what's happening with the current. And again, it's this point right in here. At what voltage did the current actually shut down? That's the number that I want to come up with. So that's what's going to show up in my data tables. I will show you the fits that I ended up with for each of the filters. Okay, so I'll get these wavelengths updated, I'll get the frequencies updated, and then I will put together these data tables. I'm the best lab partner ever, I guess, because I'm so organized with this. And then I'll put together these. Well, you guys can do the graphs. So I'll probably end up letting you guys do the graphs and do the fits. I'll give you an example of what I've done with one set of data, and then I'll probably provide a second set of data for you guys to work from. That's probably the best approach. All right, getting back to the graph that we have right here. This is our graph that says that there's going to be some threshold frequency at which we begin to see the photoelectric effect. And then as the frequency of the light gets higher and higher, we will begin to see more and more energetic electrons being produced through the photoelectric effect. That's how it works. Now, our formula that we come up with here tells us that once we've identified our data points for the 3 different filters, so we'll get 3 data points, it's not a huge number, but we're going to get 3 data points. We're going to do a linear fit, or you guys are going to do a linear fit to those 3 data points. And then once that line is drawn on the graph, it's going to tell us 2 different things. The first thing we wanted to do is we wanted to measure the Planck constant. And I guess I'll write H in here. So we wanted to come up with the Planck constant. That's going to come from the slope. If I look at this formula that I have right here, the slope of my best fit line is going to be that coefficient in front of the frequency. And hey, that's Planck's constant. Now what we can also measure is we can measure the binding energy of those electrons. And that's going to come from looking at the intercept. So that's something else you guys are going to want to report in your lab report. You're going to want to say what was the binding energy for the electrons. It's also referred to as a work function. In fact, I think in the textbook it refers to it exclusively as the work function. In chemistry they would be calling this the binding energy for an electron. How much energy does it take to remove one of those electrons from that compound or from that element? So I think that's it. I think that's everything that we need to take a look at here. So any questions, let me know. I am going to do another close-up. So I'm going to grab the camera here just a second and do a close-up. In fact, let me just do that right now. I'll just grab the camera. It's here. We can continue this. So let me bring this up and show you what all the equipment looks like. Here is our power supply. And the power supply is being used. Let me turn that on. Power supply is being used. Did I unplug it? Maybe I did. To turn on the light, it's being used to power the ammeter. We have an ammeter right here. It's a highly sensitive ammeter. It measures down into the nanoamps. I've got a... So I really am wondering if I burnt out my light. Let me check this one more time here. I may have done that. Let me stop here for a minute. I'm going to check and see if I can get this lit up, because we want to be able to see some of these things in operation. All right, we are back up and running. So there is the light. The light's turned on. There's the power supply. The power supply is operating the light. It's also operating our ammeter. And what we have right now, let me show you the current. So we do have the current. We have a sensitivity adjustment here. Looking to see, but I think we're already at pretty sensitive levels here. I'm going to move this light in closer. We talked about setting the light source at a location where we're going to start off with 100 nanoamps, and that's what we've got right now. So there's our 100 nanoamps that we're working from on the scale. And now what I'm going to do, now the voltage here is basically zero. It's like a fraction of a millivolt. What I'm going to do is I'm going to turn up the voltage. Now notice, as the voltage, I'm turning up the stopping voltage, opposing the electrons. And what's happening here is I now have the stopping voltage at a point where the current is roughly zero. And what I'm seeing on the voltmeter is about a volt. So I'm seeing 0.915 volts, or 914 millivolts. So the stopping voltage for the blue filter is going to be somewhere around that number. So I'll go back and I'll do a more careful analysis of this. And I'm going to turn the stopping voltage up just a bit more to see if we've really stopped the current. But that's what it really comes down to. So this is pretty much everything that the lab consists of. So it's you know, the voltage is actually quite a bit higher. You can see the difference now. This time it came in at 1.45 volts. So clearly I'm going to have to go back and collect more data, because I want to be very clear at what point the current actually zeroes out. And that's going to come from filling in the tables that we talked about on the board, and carrying out this graph. All right, so again, it's Planck's Constant Lab. That's what the setup looks like. If you guys have any questions on how any of this plays out, let me know. Stop by office hours and we'll get all those questions answered. And just one final set of videos here. So here's a picture of the individual filters. You can see the green, the red, and the blue filters. And then there's the photo tube. So you can see the photo tube and then the photo tube cover. So if you look inside here, you can see that rounded portion where the light shines on that, electrons separate, and then they're collected at that central piece that runs through it. So there's a little close-up of some of the other components.